Hello, this is Sarah Coffin, and this is Homework 6. So as you can see here, I have the maze up for demo, and now I'm going to start running it, running my brain code. Alright. And then as you can see here, the robot is running, and then we start to see the map over here. The map has a couple different colors on it. So it has the darker teal, which you can kind of see in the middle, and that's where there's high certainty that it's free space, so that there's not an obstacle there. The red markings on the edge, like the bright red, that's very high certainty of obstacles or walls. And then the faded in between gradient is where there's less certainty. There's also a bright green dot showing the estimated pose of the robot, but more on that later. Okay. So the robot itself is a wall follower with a couple of modifications so that it can turn corners and stuff a little bit better. So instead of turning in place, it turns on an arc with a differential in its wheel speeds, which you can kind of see here. And there's a couple other events that trigger slightly different wall follower behavior. So, yeah. Additionally, it does do a little bit of backtracking, but that's okay because the purpose of this assignment is to map area and not particularly to do it as fast as possible. All right. So, in terms of the mapping, the map structure is it's a map with key values of longs and a pair of longs to act as the x and y coordinates. These are the regular x and y double values of position multiplied by 10 and then truncated to account for a 0.1 resolution of the map. And so the map was used because it's faster to do finding and stuff like that, so it's trying to optimize it a little bit. So yeah, and additionally I can use the mplace function as opposed to just straight inserting it, so that I can create the object in place as opposed to copying. So just a little bit more optimization. So the map updates, which you can see being drawn on the screen, it updates whenever there is new information. So it doesn't redraw the map in its entirety each time. It simply redraws the cells that have changed occupancy values, or if there are new cells created. So the map struct is that pair of longs that correspond to the x and y position on the map, and then that points to a cell structure, which is something that contains a seen value, which is a Boolean, and an occupied value, which is a number. This number is added to with log odd measurements, as referenced in the associated video with this assignment from Penn State, I believe. So these log values are used for probability and certainty. So how certain it is that a wall's there and how certain it is that there isn't a wall there. And so these values are used for adding to that occupancy. And that's how you get the things like the bright red markings or the dark teal, is when they build up like that. So yeah, so whenever it takes a new measurement, if it has already seen the cell, it changes the occupancy value, or if it's a new cell, it creates a new cell and adds an occupancy value for whether it's hit something or not hit something. Yeah, and so it updates by drawing that cell, that new cell, or that newly changed cell directly on top of the map. And it only does this when there's new information, so it doesn't redraw anything. Or it doesn't redraw anything that has not changed. And this kind of serves as another way to keep the processing lower. So instead of having to redraw the map the entire time, it's just redrawing it every time there's new information. Additionally, I'm not entirely sure if you can see them, but there are 7 lines leading out from the green dot. So those 7 lines represent the LiDAR, and they follow Bressingham's line algorithm in order to fill them. So they fill, when there is a hit, they fill the free space, and when there isn't a hit, they fill the free space to the ends of the LiDAR, which is at about like 1.92 meters, or 2 units. Yes. So those values are the Bressingham line theorem, or line algorithm was used off of the Geeks for Geeks page that was mentioned in class. It's been modified to include more codes, so it's not just for slopes under 1 and from left to right. It now handles right to left, or there are functions to handle right to left, and slopes greater than 1, slopes less than 0, and all of that. So that's why you can see all 7 of the lines. Another thing that makes this different from just using the straight robot sensors is there is a little bit of localization and error handling. So that green dot I mentioned earlier, which is the estimated pose of the robot in reference to the map. So this doesn't use the straight pose X and Y values. It puts them through a little bit of a filter. I'm not entirely sure if you could classify it as such, but they are used in calculations, and then that value is then taken. And that's why the wall values on the edges are much smoother than they would be if it were just using the raw pause X and pause Y values, because that would generate a very messy map. So what happens here is there is an estimated accumulated pose change value. So for each callback, the time is taken and the velocity commands are recorded in addition to the heading. And then these are all combined to find the estimated pose change between the previous callback and the current callback. And then that pose change is added to an accumulator. And that keeps track of the overall X and Y changes in a pose structure that has X and Y fields. And then that value is compared against the given robot's pause X, pause Y, which have a lot of error associated with them. And that value, the difference of that value is then put into an X position value buffer and a Y position value buffer, which holds like the most recent 20 values. And then the mean and the variance are taken from that. And the mean is then added to the estimated accumulated position change value, and then that is what actually generates the X and Y value you see in the green dot. So it smooths out the jerky location, and it also smooths out the placement of all of the points because it's localized a little bit better. So that's what the green dot is. The green dot is also helpful because you can see where the robot is on the map as opposed to trying to guess based on what new area is being filled in. So there's that. The robot does run slow, and this is mostly to deal with the degrade velocities. As that error impacts the motion of the robot, it has a tendency to swing wildly and not necessarily get stuck, but not operate correctly. So the velocity is pretty slow. There's a modifier on it to keep it at the same ratio for all set velocity calls. Yes. Additionally, for going straight, there is an angle differential adjustment. So if the robot is going not quite straight, it takes that into account and modifies the velocity values accordingly so that it can start heading more in a straightforward direction in the direction that you wish to travel. Mainly for the north, south, east, and west values, not for the intermediate ones. So that's another thing to try and help smooth out some of the errors. All in all, it produces still kind of a fuzzy map, but it does have a general layout of the region. And it does get to a bunch of rooms, and I will continue the recording so that you can see that. And I guess be quiet for now because I don't really have much else to say. Thank you for listening, and this is my assignment. Thanks for watching. And it will, so this will continue on until we get to the acceptable number of rooms. So feel free to zoom ahead because I won't be talking anymore because I think I've said all that I want to say. So yeah, thanks again, and goodbye.